I don't silence Sina. Okay, let's do this. Just need. Yes. So, good evening, good morning, everyone, participants, and welcome to day 6 of the Newcomers for Nuclear Summer School. Today, we enter of one of the most exciting frontiers of nuclear science, advanced nuclear medicine, and diagnostics. They are not just scientific breakthroughs, they are lifelines, offering new hope in the diagnosis and treatment of complex diseases. As we explore radiopharmaceuticals and cutting-edge therapies, let's remember that behind every isotope and innovation, it's a patient, a family, a future. This is where science meets compassion, and we are honored to have us with us experts who are not only advancing the field, but also mentoring the next generation of nuclear health professionals. Let's make the most of this opportunity to learn, connect, and imagine what's possible when nuclear science serves humanity. So for today, this is the program. We have the Moroccan team representatives, Professor Nousa. She's the WiNI leader of the group. Dr. Ashban, he's also WIN Young Generation Coordinator from Mauritius. And Mr. Halid Tasman is a medical physicist, also part of the WINI members. So please allow me to introduce the great speakers we have for today. And let me just start with Mr. Khalid Tasman. Mr. Khalid is a seasoned medical physicist and the manager of the Medical Physics Laboratory at CNESTEN, Morocco, with extensive expertise in medical imaging, radiotherapy, physics, radiation protection, and dosimetry. He is dedicated to optimizing diagnostic accuracy while ensuring patient safety. Mr. Tasman has contributed significantly to nuclear medicine, working alongside renowned experts such as Professor Nousa Ben Rais Awad, and he's also an active academic serving as part-time university trainer and coordinator of the master's program in medical physics at Mohammed VI International University. Internationally recognized, he has led postgraduate educational courses in radiation protection for French-speaking countries and collaborated with the IEA to build radiological safety capacities in Ghana and Cameroon. His scientific contributions include projects on mammography quality assurance and dosimetric evaluation in PET and CT facilities. So, Mr. Khalid, the floor is yours, and we are so great to have you as moderator for today's session. Over to you. Thank you. I think you're muted, Mr. Khalid. Yes, maybe you mute yourself. Yes, in the microphone icon, maybe just press mute below left side in the bottom. Just let's wait a few seconds for Mr. Khalid. And thank you very much for your patience, dear attendees. We are so grateful to have Professor Nousa today and Dr. Ashbent contributing from the great perspective, not only in the African development of nuclear medicine, but also in different countries, how their pure experience have been improving the system and sharing the international practices of nuclear medicine. And we hope that you're enjoying session number 6 of today. Last week was a very great session where we had several topics around, and this will be the end of the week. Please don't forget that we will send the exam quiz and few questions for the survey feedback to know exactly how we did it, if everything is properly set, and so on. So let's see if Mr. Khalid is back. Mr. Khalid, can you hear us?
Yeah. I hear you and I see.
Please, over to you. The floor is yours. You can proceed with the moderation of the panel.
Okay, thank you. Thank you very much. I would like to introduce our eminent speaker and expert, Professor Nuzab Rais. Professor Nuzab Rais is the first Moroccan laureate in nuclear medicine and application to medical biology and artificial radio elements at some greatest scientific research center in Europe as Saclay, René Descartes University, and the Université of Sceaux, France. She holds master degrees in physics basis of nuclear indicators and radiobiology at Paul Sabatier University in France. She holds also a university degree in medical and biological uses of radio elements delivered by Tokyo University. She has a diploma of molecular cancer prevention at USA, Maryland. First female scientist specializing in nuclear medicine and head of nuclear medicine department. Professor, Professor highest degree in biophysics and nuclear medicine at University Mohammed V of Rabat, Morocco. Founder of University Nuclear Medicine in Morocco, more than 114 doctorate theses and more than 1,400 scientific participation. She has about 120 international scientific publications. She is an EIA expert, very involved in South-South cooperation, rich of several national and international medals, Medal Throne of Excellence and Merit ordered by His Majesty Mohammed VI, King of Morocco. May God glorify him. She is the WiNI leader since 2021. She is a very improvement woman at the European Association of Nuclear Medicine. She is Vice President of Global Health, member of several scientific national and international associations, and many other things are not listed. This is a very short CV that I have presented. Today, Professor Benoit Rice will provide and share with us general and specific information regarding theranostic topic, their application to cancer treatment, and advanced research in this field. By the same occasion, we would really like to hear from the audience, enrich to conversation, and please feel free to ask a question and share comments. Professor Rice, you have the floor.
Thank you, Khalid, for your kind words. And thank you, Florencia, and also thank you to Ashven, to Dr. Ashven, my student. I have pleasure to present you advanced nuclear medicine theranostics for newcomer in nuclear. Next, please. Next. We will discuss about general nuclear medicine, advanced nuclear medicine, hybrid imaging, and theranostic. Next. Next, please. Nuclear medicine. What's nuclear medicine? Nuclear medicine uses radioactive material called radiotracer or radiopharmaceutical. They allow us to see how organs or tissue are functioning or diagnosed, and allow us to target and destroy damaged or diseased organ for tissue in therapy. Nuclear medicine needs quality management and quality control and radiation safety. For that, we can have human resources very qualified like physicians, technologists, nurses, radiophysicists, and radiopharmacists. Nuclear medicine needs radiopharmaceutical. We use gamma ray and positron emitters. And for therapy, we use beta minus OG electron or alpha emitters. And we need equipment, and new equipment and developed equipment are SPECT-CT, PET-CT, and PET-MRI. Next. Next, please. Nuclear medicine provides relevant diagnostic and therapeutic options leading to patients' healthcare and quality of life improvement. Artificial intelligence is also emerging into nuclear medicine and promising development to use functional imaging as biomarkers are expected. Nuclear medicine is evolving at high speed. Nuclear medicine has a clearly defined role in clinical practice due to its usefulness in many medical disciplines, particularly in cardiology, neurology, and more and day by day in oncology. Next, please. Advanced nuclear medicine needs hybrid imaging, theranostic, and radiopharmaceutical. I will be able to discuss about the two first and the third for Dr. Ashfeld. Okay? Next. Next, please. What's hybrid imaging in nuclear medicine? Next. Next. And what is the difference between nuclear medicine and radiology in imaging? Nuclear medicine creates image using internal radiation waves from inside the body, while radiology develops image through apply external energy waves to the body. So in nuclear medicine, we introduce the radio element or the radioisotope inside the body. It's the big difference between X-ray imaging. And for that, we have in real time, we have how cells are functioning or heart disease in the body. And it's real time. It's very, very important. Real time information. In radiology, we haven't, because it's anatomical versus functional in nuclear medicine. And radiology is based in anatomical imaging. We can see the lesion and the disease several weeks till 6 months after nuclear medicine imaging. So in oncology, it's very, very important to do image in real time. Next, please. In imaging, the SPECT-CT, what means SPECT-CT? Single photon emission computer tomography, and hybrid imaging with CT, and the computer here is for correction attenuation and also for localization of the lesion. Currently, the best SPECT-CT are CZT detector. They are semiconductor detectors, CZT, cadmium, zinc, tellur, versus conventional detectors like iodine, sodium, that allow us to have better image contrast and superior sensitivity and higher energy resolution. This new technology may change current practice, such as decreasing acquisition time and activity injected to the patient. Next, please. Next. PET-CT, positron emission tomography, and in positron emission tomography, we detect gamma ray from 511 keV. They are produced by annihilation of the positron by electron. So it's positron emission tomography, and we detect in our gamma camera, we detect 511 keV. 511 keV is the energy equal to the mass of electron or positron. In SPECT scan, we detect only its single photon emission computer tomography, and with this single, we detect only one gamma ray, as this gamma ray is the energy of the isotope used in several SPECT scan. We use technetium. So the progress in this SPECT-CT and PET-CT and PET-MRI has boosted research and development in many areas of interest, such as oncology, cardiology, neurology, etc. Next, please. Next. The role of PET-CT is very, very important because we can have image and we can image the cells and the molecular in real time to have a good diagnosis, to have the staging. We can have staging more with nuclear medicine positron emission tomography. We can direct biopsy in the metabolic zone, and we can plan radiotherapy, and we can restage and detect recurrence, if any. Next, please. PET MRI is emerging too, and PET MRI firstly was dedicated to the brain, and day per day, it replaces PET-CT. We have an example here. The woman, the same exam by PET MRI and PET-CT in the same day, and as you see here with PET MRI, we have add pussy in the image. The PET MRI immediately after the PET-CT scan shows additional sites of peritoneal involvement in the perihepatic region, this arrow, and also in the parietal colic gutter. So if we have the best image, we can plan the best treatment for the patient. Next, please. The future in hybrid imaging, the field of SPECT-CT will take a major leap forward with CZT detector, replacing the conventional detector, allowing faster scan, better spatial and energy resolution, significantly lower radiopharmaceutic activity to the patient, allowing optimal diagnosis. PET domain will advance mainly due to the shift to digital detectors and the incorporation of whole-body PET camera and artificial intelligence. The field of theranostic will continue to advance with new indication and specific tracer, increasing the impact of our specialty on patient care. Next, please. Theranostic. Next. In theranostic, the state-of-the-art of nuclear medicine is currently based on theranostic. It consists in using the same molecule for diagnosis with gamma or positron emitter and therapy with beta minus or alpha emitter. Since 2000, the number of nuclear medicine procedures increased considerably. According to the World Nuclear Association, more than 40 million nuclear medicine procedures are performed each year worldwide. 20 million nuclear medicine procedures are performed annually in the United States. Demand for radiopharmaceutical is increasing at up to 5 and more annual percent and more annually. Thanks to progress in radiopharmaceutical, nuclear medicine has become the essential tool and the cornerstone in several specialties, particularly in cardiology and oncology. Next, please. Thanks to Dr. Solez, the father of nuclear medicine, because he discovered how to treat thyroid Graves' disease, hyperfunctioning thyroid, and how to treat thyroid cancer using the iodine. Firstly, he used the iodine 130, and secondly by iodine 131. It's the first radiopharmaceutical approved by the FDA, and theranostic has been used for more than 8 years to treat thyroid cancer and hyperthyroidism. Next, please. Next. Theranostic, a novel integrated approach that combines cancer diagnosis and therapy by switching the radionuclide, as we said. Solhers is the father of radioiodine therapy. This practice changing paradigm is effective, affordable, and practicable till now. Next, please. Next. I show you thyroid carcinoma treated in our department. In the first image, you see the image of a 48-year-old patient with bifocal papillary carcinoma of the right lobe, and the biomarker was 12. And after treatment, the biomarker was under 0.04 nanogram. So it's the efficiency of this treatment. Next, please. Other case. Can you remove your camera, Khalid, please, because you masked the picture. And here we have another case. Received 100 millicurie, 3.7 gigabecquerel of iodine 131. And the thyroid, we can see here several in fixing the iodine. They produce metastase in lungs, in liver, and in bone. Next, please. The thyroid carcinoma, we can after metastasis in thyroid cancer, we can have a remission, and the patient is treated. For this patient, it needs 2 cures of 2 radio iodine therapy and cumulative activity about 14.3 gigabecquerel, and the biomarker was initially at about 700 nanogram, and after 2 cumulative cure, the biomarker is only at 0.2. So this patient is saved. Next, please. Global nuclear medicine market in the last 10 years, and particularly it's increasing since 2013 to 2025, and particularly in the last 5 years, we have an increasing exponential increasing for therapy, for radiopharmaceutical in therapy, compared to the radiopharmaceutical in diagnosis, only 7%. So nuclear medicine, the treatment became a very important role in nuclear medicine. Next, please. The principle of theranostic is to see what you treat and treat what you see. As I said, it's image in real time. For diagnosis, we can use small molecule, peptide, or antibody. They are tracer or vector, and this tracer or vector are linked to a nuclide, gamma emitter, or positron emitter. That for diagnosis. For treatment, we use the same tracer or vector like in diagnosis, and we change only the nuclide or the isotope, allowing therapy such as beta minus or alpha emitter. This treatment consists of irradiating cancer cells to kill them while sparing healthy tissue or surrounding organs as much as possible. Next, please. So in this slide, you can see we have tracer vector, and for diagnosis, we have gallium-68, and gallium-68 is positron emitter for diagnosis, and we use exactly the same vector linker at target. It's this tracer is for neuroendocrine tumors. SSTR2 target. And we change only the radioisotope. For diagnosis, we have here gallium-68, and for treatment, we can use yttrium-90 or lutetium-177. In the picture, in the below, you can see liver metastasis and pancreatic tumor. Next, please. Theranostic objective. The goal is to combine a diagnostic test that identifies patients most likely to respond to given treatment. Next, please. So the first step, the first step is the selection of patient. I think it's the first part, the most important part for theranostic is the patient selection. In the two parts, you can optimal dose. In the third step, accessibility of a lesion study to a potential therapeutic agent. In fourth step, how to determine the prediction of response and to identify toxicity and prognosis to treatment. And in the last step, reduction of public health costs by eliminating unnecessary treatment and improving efficiency. Next, please. In this slide, you can see you have a lot of patients, but only the red patient can be candidate to receive therapy. The first step is diagnostic, and if the lesion fixed the isotope at the tracer, we can treat by theranostic this patient. So we, in our language, in theranostic, one stone kills 3 birds because it allows us to diagnose, to follow up, and to treat. Next, please. Theranostic is a precision medicine. The concept is very old of precision medicine, but actually, in the last 10 years, success of personalized medicine in nuclear medicine, this precision weapon against cancer represents not only one of the priority area of research, but also an immense hope for patients in the fight against this disease. We give the right treatment at the right patient in the right time. Next, please. If we are interested by publication in PubMed, derived number of articles including the term of theranostic from 2000 to 2020, we have an increasing, very increasing in the last 10 years, and the increasing is very important, and last 5 years since, and increasing exponentially. So day per day, the number of publication become very important. Next, please. You have in the left patient treated by actinium-225. It's the same tracer, but for diagnosis you use gallium, and for treatment we use actinium. We are able to treat this patient because all the lesions are fixing the PSMA gallium. And the marker was initially at 246 nanogram and became under 0.0 15 nanogram. So it's a success treatment. And what is the difference between chemotherapy and theranostic in nuclear medicine? It's the conventional treatment by chemotherapy and radionuclide targeted therapy is the difference between forest fire and lightning. Forest fire, all the trees are burned. And like in chemotherapy, we treat the drug is fixed by all cells, pathological cells and normal cells. But in theranostic, like lightning, we treat the lesion, not healthy cells. Next, please. Commonly used theranostic agent in therapy. The mean path length for this treatment by beta emitter or alpha emitter. By beta emitter, it's about millimeter. So it's very, very selected therapy, and it's much more interesting by alpha emitter because the path is about nanometer, excuse me. Next, please. In this slide, we have some beta minus emitters versus alpha emitters. And as you can see, the energy of beta minus emitters, it's between 0.5 to 1 MeV, mega electron volt. And for the isotope in the bottom, you have energy. It's much more important. It's about 5 to 6 mega electron volt. Next, please. So alpha emitters, it's very, very, very useful for micrometastasis because their path is about nanometers. And the energy is very important because, as you know, alpha emitters have a very, very high LET, linear energy transfer, comparing to beta minus, so they have the LET is lower. So all that conduct to double strand breaks and the cell death. So it's traducing the efficiency of alpha emitters. Next, please. You have here example of neuroendocrine tumor and several metastases and several treatment for this patient. Next, please. It's an interesting patient. We receive him in our department. And initially, in his story, he underwent surgery for right cystic hepatic. And after right hepatectomy, the biopsy, the histopathology, it's neuroendocrine tumor. But it was too difficult to localize this neuroendocrine tumor because in the first week or first month, it's very, very little lesion. So in nuclear medicine, we do SPECT-CT with the technetium octreotide, somatostatin receptor, and we see two foci of metastasis, like here in liver, and we can be able to find the primary tumor in the intestine. Next, please. FDA approved lutetium PSMA in March 23 in 2022. And actually in 2025, lutetium Pluvicto to enlarge indication of treatment. As you know, we diagnose by gallium and we treat by lutetium. And you can see here the patient with several, the first slide, the first image with several metastasis, and the PSA, the marker, was 1,160. After first cure, it decreased to 71, and after 4 cures, it's only 9 nanogram. So the efficiency of this treatment. Next, please. And the advanced nuclear medicine, day per day, we can find new target, new pharmaceutical tracer, and new isotope, and new treatment. Here you have a patient treated by actinium, by alpha therapy, and you can see after 3 cure, we have the patient has no metastasis. Next, please. For neuroendocrine tumor, you have here image after, before and after treatment. And the lutetium dotatate was approved. It's the first theranostic approved by the FDA in 2018. And for diagnostic in 2020, we have copper 64 dotatate. Dotatate is the tracer specific to somatostatin tumor, neuroendocrine tumor. Next, please. Next. What is the future in theranostic in nuclear medicine? Much more effort in targeted pharmaceutical diagnosis and treatment. In treatment, we are several trials by bismuth 212, by lead 212, by thorium, and by terbium. Next, please. Terbium is considered Swiss Army knife for nuclear medicine. Why? Because we can do diagnosis by terbium 155 to have imaging SPECT-CT, and we can use it for PET-CT if we use positron emitter terbium 152, and for treatment we can use terbium 161 or alpha therapy terbium 149. Terbium 161 is dual punch, beta particle for tumor control, and Auger electron for micrometastasis. It's a very, very good example because the same isotope, the different isotope can diagnose and give treatment. Next, please. Predicted global nuclear medicine market in theranostic. It's growing and it's increasing exponentially, particularly in therapy. And day by day, FDA approves new radiotracer for theranostic. Next, please. The benefit of theranostic, better patient care. It's fascinating to reflect on the rapid evolution that's taking place in the field of nuclear medicine. All nuclear medicine professionals highlight the 3 most significant changes in the past 5 years. Firstly, radionuclide therapy, one or novel concept. PET scan and PET MRI, the immense utility and benefit of PET scan. PET has transitioned from a specialized service to a fundamental diagnostic tool, one that should be available in every major hospital. Theranostic, the ability to see exactly what we are targeting with therapy and assess treatment response in real time, is a significant advancement. Theranostic has transformed patient outcome, enabling more personalized and effective treatment. We are in an exciting era of innovation and progress in nuclear medicine. Next, please. But theranostic has limits. The first limit is patient selection. In certain cases, the exclusion of patients likely to respond to a specific treatment caused by limitation on imaging system parameters such as spatial resolution. So, digital camera is the more important tool in theranostic, much more than old PET-CT. And this technique, theranostic, is very, very expensive technique. Next, please. Theranostic challenges, improving access and availability of theranostic globally. The real challenge for future nuclear medicine lies in manpower. To develop hybrid imaging and theranostic, we require skilled and motivated professionals. The future of nuclear medicine lies in the care we can offer our patients, and training is key to providing excellent care. And it's an unequal access to training opportunity. Next, please. In conclusion, next. Taking in account the specific needs of each patient, the theranostic approach considered as before medicine, that is to say predictive, preventive, personalized, and participatory. This area promises to increase the quality of clinical care and treatment and will ultimately reduce cost, allowing the right drug to be identified for the right patient at the right time. However, theranostic is not yet widely available because it requires different skills and facility than other types of treatment such as radiotherapy, chemotherapy, and surgery. Next. We are in an exciting era of innovation and progress in nuclear medicine. Nuclear medicine is essential, effective, evolving, empowering, ethical. And all procedure in nuclear medicine needs radiation safety and quality control. We hope that nuclear medicine continues to shine in a peaceful world. Thank you for your attention.
Thank you, Professor Nuzab Reis, for this very interesting lecture. Professor Nuzab Reis focused on a really discussed topic about theranostics. She allowed us to understand and refresh our knowledge on the subject. Thank you very much another time. I have received 3 questions from Mustafa Kofi. His question is, how can we improve PSMA PET dosimetric accuracy, gallium versus fluorine, to optimize lutetion PSMA therapy in prostate cancer?
It's very, very interesting question because isotope we have in an area or each month, we have publication about gamma emitter, positron emitter for diagnostic, particularly in prostate cancer. And for dosimetry, we can use for dosimetry we can our physicists you can respond to for dosimetry, we can use SPECT-CT. We can use because in African country we have only fluorine. In Morocco, in my country, we have only fluorine, and I don't know if the centers do dosimetry, but for best, as I said every time. If we want to be more efficient in nuclear medicine, we can go step by step. And if we do, we have standard cures approved by the FDA, and year per year, and month by month, this dose of activity of treatment decreased because each patient is when it's very, very complex because for nuclear medicine community, we have theranostic, we can treat all patients. No, the selection of patient is very, very important. And when you have the patient, we have different metastases. You can have idea about the standard uptake value or the volume of the tumor and calculated. Till now, it's very, very empiric treatment. for dosimetry is in the centers who has medical physics engineer who have qualified physicists in the department or dosimetrists in the department. Otherwise, in the other centers, nuclear medicine physician give the empiric dose. It's dose by kilogram and I agree with you. If we do dosimetry for each patient, we will be more efficient because I do dosimetry for iodine therapy in thyroid cancer. And I have if you have dosimetry, you have the effective period of the element used. You can know how much millicuri or megabecquerel or gigabecquerel you are allowed to give to the patient.
Okay, I correct the name of the person who's given the question. It's Idrissa Ouedraogo from Burkina Faso. The second question is given by Sofia Redwan. I will say integrally her message. Thank you, Dr. Ben Rice, for the presentation. My question is, what are the main examinations performed in nuclear medicine and which pathologies do they help diagnosis? Thank you.
Thank you, Sophia, for your kind words. The main pathology, it's evolving at high speed. I was involved in publication for the UNM Guide of Technologists in nuclear cardiology. And I learned a lot because there are many tracers and all the pathology, because in the heart, the common nuclear medicine exam, we have thallium, we have MIB with SPECT-CT, we have FDG, fluorine FDG, we have, and day per day. And in 2024, FDA approved fluoridipase marked with fluorine or gallium. So it's evolving. I think actually we have oncology, but neurology is emerging too in routine practice. Neurology, cardiology, oncology, all oncology, because FDG help us in lymphoma, help us much more lymphoma Hodgkinian, not lymphoma Hodgkinian, in sarcoma, in myeloma, in all. But FDG has limited. In Morocco, we have 4 radiopharmaceutical users. You have FDG, we have fluorosodium for bone, we have fluorine PSMA, and we have fluorine choline. And day per day, we demand to do our cyclopharma to give us much more element, because it's evolving at very, very high speeds. And I think actually all the cancer can have 1, 2, 3 marker or 3 vector.
Okay, Professor, you have a last question from Mr. Tamar Kalads. Thank you for your insightful presentation. From a statistical perspective, which organ cancers are most prevalent in your region and how successful are the treatment outcomes? I'm from Georgia and ask because in my country, a significant proportion of cases involve cancers of the throat, lungs, and breast.
Thank you, Tamar. Thank you, Tamar, for your statistical. In Morocco, we have a lot of hematology cancer, lymphoma, myeloma, we have breast, we have, and we have 30, more than 30 center of PET in Morocco, and half of activity in PET is for lymphoma. And breast cancer, it began to be the second one for using TEP, and prostate cancer too. But prostate cancer, it's if you have positive imaging, you can target this patient and you can give him treatment. And in my country, we have only treatment for thyroid, and we are in project to have theranostic in daily routine in the next month, I think.
Thank you very much, Professor, for all your clarifications and responses. I think
Thank you. Thank you.
there is no other question. Other questions are donc, if there is no other questions, we can move to Dr. Ashven.
Ashvet. Thank you, Khalid.
Thank you, Professor. I precise that I have learned my first steps on radiation protection and physical basics closely when I worked at your units of nuclear medicine for
Khalid.
5
And
or 6
Ashven,
years.
yes, you first. And Ashven was my student in radio pharmacy, and he is
It's
now.
an honor for us. It's an honor for us.
Yes, it's an honor for me too. Thank you.
You are welcome.
You present.
Can I shift
Ashven.
Mr. Ashven?
Yes, I think.
Okay. I don't see him.
Je suis là, je suis là.
Il
Okay.
est là.
How are you?
I'm good.
Donc, allow me to present you. Donc, you are my friend at first.
And he was your student too.
Yeah. I would like to continue the second part of this webinar with a second interesting topic, still in nuclear medicine, which concern radiopharmaceuticals. But at first, and before starting, I would like to introduce our second eminent speaker, Dr. Ashagen Sinivasan. Dr. Ashagen Sinivasan is a dedicated pharmacist and radiopharmaceutical specialist, currently pursuing a PhD at GSS Academy in Mauritius, which a strong academic foundation that includes a master in health services management. He was the first class with distinction. He holds a specialized master in radiopharmaceutical sciences from Mohammed VI University in Morocco. Dr. Sini Vassan brings a wealth of expertise to the field of nuclear medicine. He serves as a senior pharmacist at the Ministry of Health and Wellness, stationed at the Nuclear Medicine Department of Jawaharlal Nehru Hospital. His work has been recognized internationally, including a Best Presentation Award from the International Society of Radiopharmaceutical Sciences. He is mastering English and French language. He is also passionate of leadership, having participated in global forums such as the World Nuclear University Summer Institute. His CV is rich too, but time does not allow me to mention everything. Donc, Professor, Doctor, you have the floor.
Thank you, Professor Ben Rais. Thank you, Mr. Khalid.
You are
It was
welcome.
an honor also. It was an honor also to be your student, and so nice to see you here today. And thank you, Professor, for inviting me to do this presentation. Can you all see my screen?
Yeah,
Yes.
yeah. The first
Yeah.
slide.
Yes. Uh, so I think we have had a very beautiful lecture from Professor Ben Rais. She has tried to cover everything that is there currently in nuclear medicine. I know she's very passionate about it. She can speak for hours and hours and never gets tired about to talk about nuclear medicine. And for my part, I'll try to share a bit about the basics of radiopharmaceuticals. All that Professor Ben Rice have been talking about, all this is not possible without radiopharmaceuticals. So radiopharmaceutical is an integral part of nuclear medicine. Since 1940s, as we saw in Prof presentation, we have been using radioactive iodine, and we have been using ionizing radiation since a very, very long time. And it's only now that we know the real value of using radioactive elements in medicine. So as I say to my fellow patients, there's no need to be afraid of radiopharmaceuticals or nuclear medicine because whatever we are going to inject in patients, it is a very, very little amount. In terms of chemistry, when you talk about radiopharmaceuticals, you can also call them as radio tracers. You know why we call them as radio tracers is because they are injected in trace amount. That means very, very, very little amount in terms of moles when we talk about chemistry. So there's nothing to be afraid of when you talk about nuclear medicine and radiopharmaceuticals. But then it is a very delicate science. You have to be very comfortable with your subject, and especially when working with radiopharmaceuticals, when preparing them, you have to be very, very skillful. So this is not something that, you just do it. In French, we do that. We say sur le tas, but then you have to learn about it. You have to love what you're doing so that in the end, patients will benefit. So this is an image of a patient who has been treated with lutetium PSMA. And I don't know if you have heard, lutetium PSMA has just been approved by the US FDA to be used as first-line treatment also. So until recently, most of the oncologists were referring patients for theranostic treatment after they have undergone chemotherapy. Now, theranostics has been approved also by the US FDA, so it can be used before even the patients are given chemotherapy. So you see the wonders, over the years that nuclear medicine has achieved. It has been very difficult for nuclear medicine as a field in itself in the medical community to prove itself because, when you go and talk to various oncologists, they are often very, very comfortable with their chemotherapy drugs. So there's a bit of apprehension for them to move to a nuclear medicine, to move to theranostic. So that's why there's a need for education, there's a need for sensitization, there's a need for more clinical studies, there's a need for more data to show them that yes, theranostic can work. So what are radiopharmaceuticals? They are basically pharmaceuticals which have been attached with a radioactive element. So a radiopharmaceutical has both properties. It has the properties of a radioactive element, and it has the properties of a pharmaceutical also. But then there's also some kind of debate on that. In some countries, radiopharmaceuticals are not recognized as pharmaceuticals, but in many other countries, especially in Europe and the US, pharmaceuticals are recognized as full pharmaceutical. So they are governed by laws, they are governed by guidelines, they are governed by regulations, the same thing as you're producing a pharmaceutical. So a radiopharmaceutical contains a radioactive isotope which emits energy, which can be detected or used to provide an image, or it is directly therapeutic within a diseased tissue. So it can be diagnostic and it can be therapeutic separately, but it can be the same. That is what makes the magic of nuclear medicine. It can be the same at the same time. And that's what Professor Ben Rice explained. So that is what is called theranostics. So you have different energies which can be emitted by different radioisotopes, alpha, beta, and gamma. And I still remember my physics and my radiobiology lectures. So we always used to say gamma rays traveling a greater distance. So they are mostly collected, to build diagnostic information. And in nuclear medicine, and it has been like this for several years, technetium-99m is the most widely used radioisotope. It emits gamma rays of 140 keV, so not so high, but high enough so that it can be detected and a beautiful image can be produced. And it had a half-life of 6 hours. And a radiopharmaceutical consists of two components. I told you earlier, a radionuclide and a ligand. Why is it consist of two elements? It's mainly because, if you administer only the radioisotope, the radioisotope won't know where to go exactly in the body, except in the case of a radioiodine and technetium. But then if you administer technetium-99m, and if you want to see the bones, you will not be able to see the bones. You will see the thyroid, you will see the salivary glands, you will see the stomach, because this is called as normal biodistribution of the radioisotope. So without any vector, any vehicle to move it to the target organ that you want to see, the radioisotope won't get accumulated there and you won't get the image that you need. So that's why the radioisotope, and in that case, the technetium-99m, needs to be bound to some kind of vector, to some kind of ligand, to some kind of biomolecule, so that this vector can take the radioisotope to whatever organ we want to see. And if the radioisotope was a therapeutic radioisotope, which emits beta or alpha energies, so these radioisotopes would go to lesions, would go to tumorous cells, would go to cancerous cells, and by emitting those alphas and betas or Auger electrons, they will kill those tumorous cells, those cancerous cells, etc. So that's why Professor Ben Rice also said that, in the case of lighting and forest fire, why? Because when you administer a radioisotope coupled with a vector, a ligand, or any other biomolecule, it will only go to the target organ. So the target tumor, the target cancer cells, the target lesion. So it will only go there and it will only kill those cells. So that is the superiority of theranostics over chemotherapy. So that's why it makes it, let's say, more safe or safer to use theranostics rather than chemotherapy. So this is a non-exhaustive list of several nuclear medicine studies that you can perform using diagnostic radiopharmaceuticals. You can do bone scintigraphy, renal scintigraphy, MPRs, myocardial perfusion imaging, glomerular filtration rate. You can image the gastroesophageal reflux, lung perfusion scintigraphy, etc., etc. This is a non-exhaustive. There's so many different studies that you actually can do with SPECT radiopharmaceuticals. I will just take one radiopharmaceutical and explain how it works. Suppose we're using MDP. MDP is I think the most commonly used radiopharmaceutical in nuclear medicine. MDP is short form for methyl diphosphonate, and it is used for bone scintigraphies. So it is used for bone scan. So our radioisotope, technetium-99m, is prepared by binding it with this molecule, which is called as MDP. Now, why MDP? It's because simply MDP has a strong affinity for the skeletal system. So it will go and accumulate in the skeletal system. Now, when you see one bone, you can say that, nothing is happening there. It is completely static. But no, but if you zoom in the bone is very dynamic. There's always breaking of bones, reconstructing of bones, etc., etc. So there is a lot of activity happening in the bone. So when there is a particular lesion in the bone, when there's a particular cancer in the bone, a particular tumor in the bone, then there is increased activity in the bone. When there's increased activity in the bone, then there's increased breaking, reconstructing, breaking, reconstructing going on in those regions of the bone. So these radiopharmaceuticals, they will go and accumulate where there is increased activity in the bone region. So when they accumulate there, they stay there for a period of time, and that is when you can put the patient under a camera and actually visualize what is going on there in real time. So you can see in real time where exactly there is increased activity in the skeletal system. This is the chemical structure of MDP when it is bound with technetium-99m. There's a lot of, it's not just, you mix two solutions and get, the perfect radiopharmaceutical. There's actually a lot of chemistry going on, a lot of redox reactions, reducing agents, oxidizing, etc., that is going on, that you can get the perfect compound so that it can go and accumulate in the target region. Another interesting molecule is F18-FDG. But then I think most people are under the misconception that, F18-FDG is a tumor marker. But then no, F18-FDG is not a tumor marker. It's just a glucose analog. So a glucose, what is glucose? Glucose is needed by each and every cell in our body. So what happens when there is some kind of cancer, when there's some kind of tumor or lesion, then these cells have the tendency to consume more of glucose than, healthy cells. So whenever they consume more glucose, when you administer this particular radiopharmaceutical, F18-FDG, this radiopharmaceutical will go and accumulate in the cells that have the tendency to consume more glucose. So they have a high metabolism. So they need glucose as energy to provide for them. So that's why these radiopharmaceuticals, they go and accumulate in those high metabolic cells, and then we can image them using a PET-CT camera or a PET camera. This is the mechanism through which the radiopharmaceutical is trapped inside. So actually the 18-FDG is a bit of a camouflage. When it enters the cell, it doesn't go through the normal cycle that a glucose molecule will go. So we try to dupe a bit the cell. So when we administer the FDG, the cell will think that it is glucose. It will take it in, But then when it takes it in, it will immediately realize that no, this is not glucose, and this will be trapped inside the cell. So that's how we can actually image the cells that are accumulating 18F FDG. So I told you earlier there are mainly two main types of radiopharmaceuticals: diagnostic and therapeutic. Diagnostic radiopharmaceuticals are used for imaging procedures, while therapeutic radiopharmaceuticals are utilized for targeted radiation therapy. So the preparation, I told you earlier, the preparation involves complex procedures. There's not, a standard SOP to prepare all the radiopharmaceuticals are the same. There are some pharmaceuticals which needs to be boiled. There are some pharmaceuticals which needs, which needs to be added some buffer, some acid, etc., some alkaline, etc. So all of them have different preparation procedures, but it's not, simple mixing. It's accurate preparation of radiopharmaceuticals. You know what to put, when to put, how much time do we need to shake. All of this is important because in my practice, I see that whenever nuclear medicine technologists are preparing radiopharmaceuticals, they have the tendency, to forget about the SOPs in place. Whenever you need to boil for 10 minutes, to save time, they boil just for 5 minutes, and then they think that they can administer the radiopharmaceutical, because at the end of the day, they think that whenever they get a clear liquid, everything is all right. But it's not that. I have started to do quality control. So when you do quality control, you see how much of the radio labeling has occurred or not. And for a radiopharmaceutical to be acceptable to be administered, at least 95% of the radiopharmaceutical should be labeled with the radioisotope. So that's what I told you. Stringent quality control measures are implemented to verify the purity, stability, and radiochemical identity of radiopharmaceuticals. This includes rigorous testing of radiochemical purity and sterility to ensure safety and efficacy. Sterility is as much as important because those radiopharmaceuticals are meant to be administered parenterally, intravenously, so directly into the systemic circulation. So that's why they are to be regulated, they are to be controlled the same way as you control all of your IV administered drugs. So radiopharmaceuticals have diverse applications, including imaging techniques such as PET and SPECT, as well as their targeted therapy for conditions like cancer and thyroid disorders. Their versatility and precision make them invaluable in modern medical practice. So since the breed of radiopharmacist is very rare, I don't know many radiopharmacists. So this is a bit of what the duties of radiopharmacists are. They are mainly involved to ensure that the radiopharmaceutical is prepared in the correct way, and they also give assurance to the nuclear medicine physicians that whatever is being injected in the patient is safe, and it is the correct radiopharmaceutical, and it is labeled adequately. At least 95% of labeling should occur. Whenever we talk about diagnostic radiopharmaceuticals, it can seem not important, these labeling efficiency. But just imagine when we talk about alpha therapies and you get a labeling efficiency which is not adequate, you will have free alpha particles everywhere. And this is not at all acceptable in nuclear medicine. So that is why stringent SOPs are important, and stringent quality control also are important. That's it for me. Thank you. If you have any questions, you're most welcome.
Thank you, Dr. Ashvan, for your clear and nice presentation. For the moment, I have no online question, but I don't know if there are some participants who hope to give some question or remarks, or we can wait 1 minute.
Yes.
There is no online question. Can I
Thank
ask?
you, Ashwin, for this very clear presentation.
Can I give a question as a medical physicist?
Yes. Yes, as medical physicist, you can. I don't know where in some countries the authority are very conscient of the presence of radiophysicists, but not for radiopharmacists. And if we need to give good practice, and as Dr. Ashwin said, good practice and SOP, I think we must have radiopharmacists too. And it's impossible to begin by theranostic in prostate cancer, into neuroendocrine tumor without radiopharmacist. I think it's one of the backbone of human resources in the nuclear department, nuclear medicine department. If we want to do good practice, and if center wanted to be a center of excellence, they must have a radiopharmacist.
Yes, I completely agree with you. And
thank you for your very clear presentation.
Thank you. And I think the IAEA also has just published a guideline for radiopharmacy education. So anybody who wants to read it, it's very nice. So I think now they are realizing the importance of having radiopharmacists everywhere in every nuclear medicine department.
Okay. Can I ask my question?
Yes.
Okay. For a long time, I've been asking myself the following question: what is the difference between MDP and HMDP, and why do some physicians prefer one over the other?
I didn't hear you. Can you repeat?
Okay. For a long, wait.
The difference between HMDP and MDP.
And why some doctors prefer HMDP to MDP?
I can respond. Yes,
okay.
Ashwin?
Both of you can give a response.
In my knowledge, I am not radiopharmacist, but I can respond. The HMDP is much more specific for bone skeleton than MDP. MDP was first. We have, but the best one is the DPD, but it's very expensive. So if we have the chance to have HMDP, it's much more better than MDP. And if we have chance to have DPD, it's the best one.
Okay. And a short question, another short question. How do you see that we can install a certain synergy between radiopharmacists and medical physicists?
I think it's very important first that they work together, because if you're when Prof was answering the questions about dosimetry, without radiopharmaceutical, what dosimetry will you have? You need radiopharmaceuticals first to do dosimetry on patients, right? And to ensure that your dosimetry is right, you need to be sure that the radiopharmaceutical is right, that the radiopharmaceutical is prepared correctly, right? So I think they need to work you know, together, both hand in hand, especially when you're talking about theranostic using alpha. So
yes,
so I think
very true.
in one department, in the first slide of Professor Ben Rai's presentation, it's there. You need to have the physicians, you need to have the physicists and the pharmacists.
Radio pharmacist.
Yes, radio pharmacist.
Radio pharmacist, not
As
pharmacist.
long when you're in a diagnostic setting, then you can say, okay,
Yes,
it can go. But when you shift to using, therapeutic radiopharmaceuticals, then I think it becomes more. It becomes a legal issue also. Who will be
yes,
accountable? Who will be responsible at the end of the day? The doctor cannot be responsible for everything, right from preparing the radiopharmaceutical and administering it, and everything.
the
Okay. I
driver
just
is
received
the
a
head.
question from I just received a question from Najwa El Ghazali. She says, what are some key factors to consider when developing a new pharmaceutical formulation, such as a tablet of or capsule, to ensure optimal bioavailability and therapeutic efficacy?
Okay, so in nuclear medicine, we don't normally use tablet or capsules for radiopharmaceuticals. But then you have liquid iodine, which is encapsulated, so that it gives you the ease to swallow, ease to transport, etc., and ease to administer to patients also. So that is the only formulation that we have in nuclear medicine that is in capsule form. If I'm not wrong, Professor, right? That is the only one that we have.
Okay.
Can have capsule for iodine therapy.
Yes, capsules for iodine therapy. Yeah, that's what I'm saying. That is
I think
Lawrence impatient.
there's,
I'm
okay.
here.
I think it's okay.
Yes, I'm here. Yes, I was just saying that, that is the only formulation that we have as capsule that is radioactive iodine. And it is only because it is easy to administer to patient, and only because it is easy to transport also. That's why we have it in capsule. There's no other thing or other factors which affect that.
Florencia wants to speak, I think.
Okay.
Yes.
Okay. Your floor.
Yes, just maybe short closing remarks, maybe an opinion about all the experts in this panel. What do you think will be the critical needs in every country, or at least in general, for the radiopharmaceutical sector in nuclear medicine? Because we know from country to country the capabilities are different, but maybe few technologies that maybe can help us to accelerate more both, I mean, the entire sector in nuclear medicine. Maybe if all of you can share your perspectives for the future, maybe the coming 5-10 years. Thank you.
I think, it depends. It depends in which region you're staying. Because if you stay in Europe, then the accessibility and affordability of radiopharmaceutical is just another question. If you stay in a country like mine, a small island off the coast of Africa, it's very difficult for us to access radiopharmaceuticals because we don't have any nuclear reactor, you know, uh, in our country, etc., etc. We have one cyclotron, but then we rely on collaboration between several African countries so that we can get our radiopharmaceuticals. But I think it is all a matter of whether or not the industry really wants radiopharmaceuticals to be accessible to everybody. Because right now, when we are speaking, it's not easy for Africa to afford therapeutic radiopharmaceuticals, but I know it's very expensive in Europe also. But then just imagine the price for us here in Africa. So maybe what we should do, I'll speak for Africa because I love Africa also, and I live in Africa also. What we can do is uh, we need to have some sort of uh, by Africa for Africa collaboration so that we can produce in the African continent. We can have our own regulations in terms of radiopharmaceuticals, and we can use it here for our patients. But there's no need to rely on any external factors, on any external countries, so that we can be self-sufficient in terms of radio farmers. I know we have the willpower, we have the people who are willing to do it, but then we just need, the driving factor. That's it. I think Prof wanted to add something.
Okay,
Yes.
thank you very much for your nice conferences. I have to say that these two conferences complement each other and will enrich the knowledge of participants for summer school of this year. I don't know if Florencia, Professor Bonrais, or Mr. Ashvin, you have some word to say before closing the webinar.
Just to thank enough Florencia, to thank Eva Jeanne, to thank you, and to thank to Ashwin. And in the new department, the big department of nuclear medicine, I have the chance to head. We can have PET MRI, PET CT, and SPECT CT, and it will be a center of excellence in nuclear medicine in Morocco and Africa. And for that we can have a cyclotron near the hospital, practically inside the hospital, because we have in Morocco 2 cyclotrons, and the third is in the future Mohammed VI hospital. Thank you very much, Florencia. Thank you very much, Ashwin. Thank you very much, Khalid.
You are welcome, Professor.
Thank you very much, Dr. Nisa, for being a great pioneer in nuclear medicine in Morocco and a great inspiration, not only in Africa, but for many experts and specialists in the field. I think you are a role model to follow. And yes, over to Dr. Ashpan before we set up some closing remarks.
I think it's already late, so I'll just say thank you to Prof. Ben Aish, thank you, Florencia, thank you, Eva, thank you, WiNI, thank you, Wing Global, thank you, Mr. Khalid.
So thank you to all participants too.
Yes, thank you to all participants too.
So thank you very much for your presence and participation today. The insights shared have shown us how nuclear medicine is transforming healthcare, making it more precise, more personal, and more powerful. So let's carry forward the knowledge and inspiration from today's session into our own work and communities. And the future of nuclear medicine is not just in the laboratories, it's in our hands. So we look forward to seeing you tomorrow as we continue this journey of discovering a collaboration. Until then, stay inspired and connected. Please, Lancina, over to you if you would like just to set up some few words before we leave. Thank you.
Thank you to Lancina too. Thank you, Lancina too.
Good evening. Good afternoon.
Good evening.
Yeah, I'm Lancina too. We share a lot with Professor Nusa. Professor Nusa, the mother of medicine nuclear in Morocco, in Africa. Thank you to have you for a more small minutes in this open university for the world. It is very, very wonderful for us to have you and to have your brilliantissime doctor student, Snes Vassen from Mauritius. And we like to thank you, Khalid Tasmat. I know where you propose the two specialists, Khalid Tasmat and Dr. Snevesen. It is a very, very wonderful these days to spend a lot of time with you and to learn, to understand everything. It's not the whole, but it is a start point, to introduce medicine nuclear in our summer school. Thank you so much. I would like to congratulate everybody that take care of this summer school, that work in the summer school, that present in the summer school, that moderate in the summer school. Thank you so much.
Thank you. Thank you very much.
Thank you, and God bless you. We see you tomorrow morning and evening or night, depending where you are. And thank you very much for the brilliant participation and engagement. Have a very good rest of your day. Thank you.
Thank you very much.
Thank you very much.
Bye-bye.